So today we're going to take everything that we've done in the last couple of days and combine it all into one. We're going to do combining transformations today. What I mean by that is we're going to take vertical and horizontal translations, left, right, up, and down, and we're going to combine these with vertical and horizontal stretches where we're making things taller and wider or thinner or shorter or whatever, right? We'll also throw some reflections in here as well. So we really truly are taking everything and putting it all together. Here is today's plan. So like I just said, throwing everything all together all at the same time. In doing so, we have to talk a little bit about the order of operations for function transformations. In other words, when you do translations and reflections and stretches, what do you do first? What happens to the function first? We'll talk about that. We'll also create equations in both function notation and equation notation for transformed functions. Hopefully you remember that function notation is absolutely perfect for a starting point. Even if I don't ask for it, it's always nice to start in function notation and then go to equation notation from there. Lastly, we'll finish up today by looking at mapping notation and transformations. So how to use mapping notation when we have all of these kinds of transformations applied to something. It's going to be a busy day today, but let's get rolling. So with transformations, just to do some full thorough review, when you're combining two or more transformations, consider the following parameters when y equals f of x is transformed to this right here. This form that I've got right here really ties everything all together. You have your a, your b, your h, and your k, and those represent some stretches and some translations. In other words, some shifts left and right. Let's break down each of these parameters, though, make sure we know what they mean. Let's start with A, the very first one we see here. A causes a vertical stretch, and we know it's vertical because it's on the outside of the function. It's not inside f of x, it's on the outside of the function. So it causes a vertical stretch by a factor of A. So in other words, you're literally multiplying by A across the x-axis. Vertical stuff goes up and down, so it's crossing that x-axis. If I just drew one up here, since it's going vertically, it's crossing that x-axis. If it is negative, it also causes a vertical reflection. So if you have a negative a value, if this thing is like -4, not only is it stretching it by a factor of 4, but it's also doing a vertical reflection. So it's flipping it across that axis. Now B, this is the worst one in my opinion. B is an absolute nightmare, but B causes a horizontal stretch. We know it's horizontal because it's on the inside of the function. And this is where the absolute nightmare comes in. It does so by a factor of 1 over b. In other words, it does it by a reciprocal of b. Now, horizontal stuff, this happens across the y-axis. And if your b value is negative, this also causes a horizontal reflection. So very much like the other one, the biggest difference, of course, is how the factor plays a role here, right? So it's not multiplying your x values by b, it's actually multiplying them by 1 over b. Excuse me, here I go sneezing 3 minutes into the video. My goodness, my apologies. Anyway, next one, h. Notice h is on the inside of the function as well. Since it's on the inside, we know it's a horizontal. And because it's adding or subtracting, it's a horizontal translation. In other words, a shift. If h is greater than 0, so if you're going like x minus some positive number, so x minus 5, well, since it's x minus 5, minusing means it's going right. So when h is positive, it goes right. And if h is negative, so if we went like x minus -3, well, x minus -3 would be like x plus 3. That's moving it to the left. All right, and then the last one, k. Notice k is on the outside of the function. That tells me it's a vertical translation, or in other words, a vertical shift up or down. If k is greater than 0, then the graph is going to move up. So if k is a positive number, the graph's going up. If k is negative, so if k is less than 0, then the graph moves down. Really important that we know all these parameters. All 4 of those parameters there are super important. Some are a lot trickier than others, but you know, it is what it is. Now, applying to equation notation, sometimes in the past, I've seen it's been kind of tough for some students to figure out where things actually go. Just remember, we have a lot of common base functions that we often use. Here's just 4 of them. If you were to apply all of these parameters to a base function of each of these, basically you just need to realize, because we are changing the inside of the function with the stuff, I'll just flip back with this stuff that you saw inside the f of x, you are just replacing the x in each of these with that stuff that was inside the function. So if you had this, it would become y equals a times b times x minus h with some nested brackets in there like so, really important. We'll talk about that later today. Squared, so it's like this thing becomes your new x and it's being squared, and then plus k. What I really need to illustrate here is all of your vertical stuff, so a and k, they're happening outside this function altogether. So they're beyond where this x squared even was in the first place. Same goes with these other ones. They all kind of compare in a similar way. The bottom line is you just replace the x with whatever was inside those inside that function, inside of function notation. And that's why it's so useful having function notation first, because it gives you a starting point, and then you can see what you're replacing x with. Anyway, moving on. So here's an example. Suppose the base function y equals x cubed was transformed by vertically stretching it by a factor of 3, horizontally stretching it by a factor of 2, and moving it left 7 units, and then moving it up 5 units. Holy smokes, we got a lot of stuff going on in this one. Create an equation for the new transformed function. Now, generally speaking, if we see the word equation, it means equation notation. And especially since we were given what the base function is, we got to go to equation notation here. But despite the fact that we're talking about equation notation, it's always a good idea to start with function notation, even if I didn't ask for it. It's always a really healthy start point. So I'm going to do that. I'm going to say function notation first, even though it was not asked for. Let's take all of our parameters in play here. If I look through the numbers here, vertically stretching it by a factor of 3, that would be my a value. Horizontally stretching it by a factor of 2, that would tell me b is not equal to 2. That's our factor, right? B is the reciprocal of this, so b would be 1 over 2. That's always really sneaky, right? Moving it left 7 units, that's my h value, but since we're going left, we have to make sure it's x plus 7. We'll keep that in mind. And then moving up 5 units, well, that's my k value. All right, so in function notation, we would say that this is y equals, you know what, I'll write the general form of this first. Y equals a f b x minus h. Notice I use nested brackets there, so I put like a square bracket, b, and then more brackets surrounding x minus h. There's a reason for that. We'll get to that in a minute. Plus k. So a is 3 as we found here, so I'll say it's 3 f, and then b is 1/2, so 1/2 nested bracket x minus h, but since it's going left 7, I'm going to say that's x plus 7. And then k is on the outside of this, so I'll finish those nested brackets off, plus 5. Now, here's why I like starting with function notation. Now I see what's inside the function. That stuff there is going to replace the x in the base function. So when I switch now to equation notation, we just need to replace the x in the base function with this stuff in here. I actually like doing that first. So I'm going to give myself a little bit of space. I'm going to say y equals, I'll give myself some space so I can get some other stuff going on out here. Instead of writing x cubed, I'm going to write 1/2 times x plus 7. So basically just copying what I had in here. Then that gets cubed because this stuff is replacing the original x. And then we have a plus 5 on the outside, as well as a times by 3. The f disappears because the f is just referring to the fact that this was our original function. It's 3 times the original function, just with this replaced as x, plus 5. So 3 times the original function, where I replace x with this stuff. So notice the x cubed is here, right? So it's this stuff replaced with x cubed, plus 5. And that's it on that one. That is how we get to equation notation. Having function notation is a really good help, at least in my opinion. You didn't have to do it in this case, but for me, I like doing it anyway. It certainly doesn't take too much extra time. Anyway, moving on to the next page, we're going to talk about order of operations here. So in other words, when we sketch functions with a combination of transformations from an equation, we have to follow the order of operations rules, unless we're told to do so in a particular order. And then that's where things get a little spicy. We might deal with that another time. But basically, when you are doing transformations on a function, you need to deal with stretches and reflections first. Now, the reason for this is you might remember order of operations in just general algebra is BEDMAS. And in BEDMAS, you got to do your brackets and your exponents first, and then division and multiplication and addition, subtraction. Well, long story short, stretches and reflections both involve multiplication. And that happens before translations, in other words, moving things left, right, up, down, because those involve addition and subtraction, which take place after multiplication in BEDMAS. Now, another really important thing, and I've already illustrated this, or at least told you a couple times, always express your function in this form. So this is our function notation form. Always express it in this form. Most notably, make sure there are nested brackets inside the function here. So b should not be like right up touching x, especially if there's an h in here. There should be some brackets separating it. Now, if there isn't an h value, then I guess it's okay. B and x can be bumped right up against each other. But if there is an h value in here, make sure b is factored out of there so it's not affecting it directly. Now, like I just said, watch those nested brackets carefully. Without them, the horizontal translation, in other words, 1 over b, becomes much harder to interpret. We're going to investigate this right now, actually. So here's an example, both without and with nested brackets. So the following, this graph right here, the following is a graph of y equals 2x plus 6 squared. Here's my first question. What is the base function here? What do we do, or what function do we base all of these transformations off of? So remember, strip away any of the weird stuff happening to this. What you'd be left with is just y equals x squared, just a basic quadratic. That would be our base function in this case. Now in words, what has been done to the base graph? Now, there's a couple things. First of all, we have like a multiplication inside the function. That would be like our b value, right? So since b is 2, that tells me we have a horizontal stretch by 1 over 2. In other words, we made it half as wide as it used to be. And it kind of does look kind of like thin in this case. So we did make it a horizontal stretch by 1/2. But then we have this plus 6. Now, to the untrained eye, if you're looking at this function, you might say, oh, well, there's a plus 6 in there. Plus means going to the left, so we must be going left 6. But notice on the graph that I gave you, compared to where the vertex usually would be, vertexes on an x squared function are usually right at 0, 0, but this one just moved left 3. It didn't move left 6 like this would intend. It looks like it actually just moved left 3. Well, our eyes aren't deceiving us here. What we're seeing on the graph is actually the true representation here. So I'm not going to say that it went left 6, because clearly it didn't. In words, it actually went left 3. But here's the question. If it went left 3, why does it say plus 6 inside of this function? Well, here's why. Remember, I've said a couple times today, you need to have nested brackets separating your b value from the rest of the stuff inside your function, especially if you have an h value, which is what you've got right here. Since there aren't nested brackets, in other words, since there's not something like this in here, this whole function gets thrown away because we can't tell, at least not immediately, by looking at it, what kind of a transformation has occurred. The b value is still fine. We can see b is 2, so therefore we have a horizontal stretch by 1/2, but the other stuff is kind of, missing, right? So the question says, rewrite the function in equation notation, so this function here, using the proper nested bracket form. Now to do this, you just need to factor out the b value. Maybe I'll even write that here so you have it. Factor out the b value. That's what you got to do here. Ooh, value, there you go. So the b value here is 2. We just need to factor 2 out of these brackets here. Now we can't literally take it straight out of this because we can't remove it from a squared. It's got to be stuck in there either way. So here's what it's going to look like instead. We're going to have y equals bracket. I'm going to take the 2 out of each of these. It's still going to be inside brackets here, so the squared will still hit it, but I'm just going to remove it out. And then I'm going to put a nested bracket in here. So in other words, another bracket inside these brackets. If I take 2 out of each of these, 2x divided by 2 is just x, plus 6 divided by 2 is 3. Then I can close that off, close off the other bracket, because now we're on the outside here, and then squared. Just to make sure we did this correctly, imagine if you undid that. If you double dip that 2 back through, you would have 2x plus 6 and then squared, which is exactly what we started with, right? Now that we have nested brackets, though, this kind of more jives with what we see in the actual graph, right? So we have our b value is 2, so we still have a horizontal stretch by 1 over 2. But this time around with these nested brackets, it's a lot more clear that we're actually going left 3. So we can see that much better. This is a good example for illustrating why those nested brackets are super important. If you don't have nested brackets in a question, you need to change it so that you do, because otherwise you're just going to be thrown off by this thinking that you're actually going left 6, when in reality you're going left 3. Anyway, let's march on. So here's an example. Describe how the graph of the function y equals blah, blah, blah relates to the graph of y equals the square root of x. So let's analyze what they did. This is our base function. Let's analyze what they did to it. There's a 3 on the outside of the function. That's probably a vertical stretch right there. There's a 5 on the outside of the function. That's probably a vertical translation. But then notice the inside of the function. What do you notice here? We have a b value, and then we have like an h. But what do we not see? Well, hopefully you'll notice we don't actually see nested brackets. So let's fix this up. Let's make sure we get nested brackets on this first. So this is going to give us y equals, the 3 on the outside is fine, but then we have the square root of 2 bracket. Let's take 2 out of each of these. So that'll be x minus, divide 2 out of this, it'll be minus 3. And then we'll have that plus 5 chilling on the outside there. Now that we have our nested brackets, we're good to go on this one. So in terms of describing how the graph relates to the other graph, we can just describe the transformations here. 3 is a vertical stretch, so we'll say a vertical stretch by 3. The 2 here is related to a horizontal stretch. Remember, horizontal stretches are backwards, so horizontal stretch, not by 2, but it'll be by 1 over 2. Then we have a x minus 3 here. What way does minus 3 go? Well, that would be right, so it's going to go right 3. And then we have a plus 5 on the outside. I think that's always the easiest one. That's just up 5. Awesome, right? Without nested brackets, it can really throw us off. You might have thought that we were actually moving right 6. We're not. Believe me, we're not. If you wanted to graph both of these, you would actually see, well, sorry, if you graph both of these, they'd look the same. But if you wanted to graph the base function and then either one of these, you would see it actually is indeed moving right 3. But that's on you if you wish. Okay, a few more questions. We're actually making reasonable time today, knock on wood. The graph of f of x equals x squared, so there's our base function, is transformed to create this. Holy smokes, this is function notation because we have an f here, so this is function notation. Describe the transformations that occurred to f of x to get g of x, so this is our new function, and then represent g of x in equation notation. Okay, so it just wants us to describe in words the transformations. So let's break this apart. We'll worry about the second half in a moment. If we're to break this down in words, let's start with some of the easier ones. Look at the outside of the function. We have a vertical stretch by 2. So a vertical stretch by 2. That one's not too bad. Notice on the inside of this function, we have our nested brackets. That's perfect. That's a really good sign. We didn't have to panic on this one. We have nested brackets, but notice our b value is 1 over 2. The b value is not our horizontal stretch, but it is the reciprocal of our horizontal stretch. So our horizontal stretch here is not 1 over 2. It's the flip of that. So our horizontal stretch is 2 over 1, or in other words, just 2, right? So that's kind of nice. Then we have plus 5 inside here. Think about which way that's going. That's going left 5. And then we have a minus 8 on the outside. That's going down 8. Awesome. Okay, so we have all our transformations there. Now it wants our equation notation. Let's give it what it wants here. So equation notation, this just basically means take all of this junk and put it into this right here. I always start with the inner stuff. This stuff inside the brackets is going to replace my x directly. So I can say g of x, that's the name of this function. If you prefer to just say y, it's up to you, but whatever. G of x equals, change the inside of the function with this stuff. So it'll be, I'll give myself some room here. It'll be 1/2 x plus 5. This stuff is replacing x here. So that's where x is. We'll just put a squared on that now because it's like x squared. So this is all squared. And then we have a minus 8 on the outside. And we also have a 2 multiplying this as well. So 2 right there. And that's it. That's your equation notation right there. So starting on the inside and working your way out, forgetting equation notation, that often is a pretty good idea. All right, we're going to do a couple more like this. Here's the next one. The following transformations are applied to the base function this. That's a really gross base function. Base functions usually are just like y equals x squared. This one's kind of gross, but we can manage with it. This is why we're doing this one on purpose. So here's the transformations. It gives it to us in words. A reflection across the x-axis. Let's just hold on a second here. If we're reflecting across the x-axis, this is the x-axis here. If we're reflecting across that, that would be a vertical reflection. Now, the reason that's important is, remember, reflections are where we multiply by -1. Since it's vertical, this means my A is negative. Good to know. Next one, a vertical stretch by a factor of 1/4. There you go. There's your A value. Nice. But we know it's not going to be just 1/4. We know A is also negative, so it'll be -1/4. But there you go. So maybe we'll even write that. A equals -1/4. Awesome. We got one of our letters down already. Then we have a horizontal translation left by 2 units. That just means on the inside of the function, we'll have a +2. And then a vertical translation down 3 units. Well, that just means on the outside of the function, we'll go -3. Write an expression in equation notation that represents the new transformed graph. Here's something. Remember what I said? I think it was one of the very first things we did today. It's asking for something in equation notation. That doesn't mean you don't have to do function notation first. I would absolutely 100% start with function notation. It's always a good starting point. It gives you the foundation for the rest of the problem, right? Even though it doesn't ask for it, it's always a good idea. Anyway, starting with function notation, remember function notation will always look like y equals a f b nested brackets x minus h plus k. Just copy that in there. We know what our a is. A is -1/4. So I'm going to say y equals -1/4. And then we'll write f bracket. Let's think. Do we have a b value here? B values are related to your horizontal stretch. I don't see anything in this question saying we have a horizontal stretch. So guess what? B is just 1, right? We don't even have to write it in there. So I'll just say forget it. Then we'll do x minus h. I don't really need the nested brackets here because we don't have a b value. So there's no danger there. So I'm going to go x minus h. Well, we know that's our horizontal translation. Well, we're going left 2 units. So really it's going to have to be x plus 2. There we go. And then a vertical translation down 3. That's going to be our k. So it'll be -3. Just double check. A is negative. We got that. A is -1/4. We got that. Left 2 units. We got that. And vertical translation down 3. Yeah, we got that. So we're all good. Now, for the thing it was asking for in the first place, equation notation. Once you have function notation, getting that equation notation is much easier. Remember, start by replacing your x in your equation notation. Start by replacing your x with whatever was inside your function notation. Let's do this. So it's going to be y equals, I'm going to replace x here with x plus 2. So I might as well write 2 times x plus 2 squared. So it's like I changed the x to an x plus 2. And plus 1 was still in the original function there. So there's a plus 1. So we've taken care of the inside of the function now. Now notice the other stuff we have is a multiply by -1/4 and a -3. Well, that happens on the outside of the whole function. So guess what? I'm going to put brackets around this whole thing. And we'll do -3 out here and multiply by -1/4 out here. So just to repeat what I did again, I took the x plus 2 on the inside of the function and I replaced x with that x plus 2. As for this -1/4 and this -3, they happen on the outside of the whole function. So in other words, this whole function gets dealt with first, and then we have a -3 on the outside and a multiply by -1/4 out front. The other ones didn't seem quite as bulky because the other ones we looked at didn't really have like a +1 to them. They were just one single chunk. That's all we were replacing. But that +1 gets caught in the mix here because it also has to be moved down 3 and so on. Definitely a tough one though. But again, this is the power of function notation. It helps to make it a lot clearer where we're going with things. All right, last question here. We're going to deal with mapping notation just because we haven't really dealt with that much, if that even at all today. I don't think we even talked about it at all today. Here we go. So mapping notation, like I will remind you again, is very important for moving individual points, like individual coordinates, one at a time. So here's an example. This is a 4-part example, right? Given that the point P, which is 6, -8, is on the graph of y equals f of x, whatever f of x is, we weren't given the equation here, state the mapping notation of the transformation as well as the new coordinates of the corresponding image point for each, right? So by corresponding image point, I mean we're moving point P somewhere else using whatever's happening here. Well, let's think about what's happening here. This one first, y equals 2fx plus 3. Think about it in words, what's happening to this. It's a vertical stretch by 2, and we're moving it left 3. Let's get mapping notation first here. xy is going to become, think about what's happening to our x here. What are we doing in the horizontal direction? Well, we're moving it left 3. This might seem a little backwards, but since we're moving it left 3, that means x is going to be minusing 3 from it, right? Because we're going left 3. So if your old point was at 6, our new point, since we're going left, is going to be at 3, okay? Because 6 minus 3, 3, right? Anyway, as for our y, the only thing happening in our y direction is this vertical stretch by 2. So our y is going to be multiplied by 2. If we're going to move our point 6, negative 8, watch how nice this is now. We have 6, negative 8. Just apply your mapping notation to it. X minus 3, so 6 minus 3 is 3. 2 times y, 2 times negative 8, well, that's negative 16. Awesome, right? We moved a point. Now let's try this next one. This one has a different kind of transformation on it. Think about what this negative out front means. This negative out front means we have a vertical reflection. A vertical reflection. If you are reflecting something vertically, you are multiplying its y value by -1 to flip it over, right? So y value is being multiplied by -1. As for this 3 on the inside of the function, that's related to a horizontal stretch. But remember how backwards horizontal stretches are? That's going to be a horizontal stretch, not by 3, but by 1/3, right? So this is going to be xy becomes horizontal stretch by 1/3. This is going to be 1/3x. And then we have a vertical reflection on y, so that'll be minus y. Now, if we're going to do this with this point, 6, negative 8, that's going to become 1/3 times 6. Well, that's just 2. Negative 8, well, that's just positive 8. There we are. Nice. Anyway, moving on. Next one. Almost done. This is the last new slide. Here we go. First of all, y plus 4 equals this. Get out of here with that garbage. We don't want plus 4 over there. We'll move it as a -4 over here. So I just took it away to the other side. In plain English, what's happening here? This one's actually simpler. This is kind of funny that this is question C here. In plain English, what's happening? X minus 2 on the inside of the function. What way is that moving? Well, that's moving right by 2, and this is moving down 4. So here we go. We're going to take our xy. We're going to move it right 2. Remember, this is kind of backwards, but if we're making something go right 2, that means 6 is going to head to 8. So we actually had to add 2. So it's going to be x plus 2. And then we're going down 4. That's exactly what it sounds like, though. Y minus 4. Now we're moving this point again. 6, negative 8. This is going to become 6 plus 2. That's 8. And then negative 8 minus 4. Well, that'd be negative 12. All right, the last one. This one is the beefiest of them all. First of all, notice all the junk that's happening over here on y. Let's move it all over. So I'd minus 6 on both sides. And then we have to divide by 3. But dividing by 3 kind of makes things, kind of tough. So instead, we're going to have to just multiply everything by 1/3. I mean, if you think about it by dividing by 3, that's fine as well, but whatever. But anyway, when we times by 1/3 or divide by 3, whatever you want to do, we have to hit both of these pieces here. So be really careful. This is going to give me y equals 1/3 f of negative x minus 1/3 times 6. Well, that's going to be minus 2. Now, since we've cleaned this up a bit, let's think about what's happening here. This 1/3 out in front, that's a vertical stretch by 1/3. So that'll be affecting our y value. This negative inside here, that's just a horizontal reflection. So it's going to be making our x negative. And then we're going down 2. So let's put this into mapping notation. xy becomes, in terms of an x direction, the only thing happening is that negative x. And that's literally going to be a negative x there. It's probably the only thing in the horizontal motion that actually acts the way you'd think it would. And then in terms of y direction, we're multiplying our y values by 1/3. So 1/3 y, and we're also minusing 2 from it. Awesome. I'm running a little bit out of room here, so I'll do this over here now. 6, negative 8. That's going to become negative 6, negative 6. Whew, and then this one's tough. 1/3 times y, so 1/3 times negative 8, well, that would be negative 8/3. And then minus 2, just for fun, remember, the only way to subtract fractions is to have a common denominator. So I'm going to write that as minus 6/3. So this will clean up to negative 6. And then negative 8 minus 6, so that would be negative 14/3. And there it is. That's where that point has moved. Whew, wow. Still a pretty long lesson today. That was about half an hour long. For practice, I cannot stress this enough, but page 38, questions 1 to 8, 10, and 11, I know they're textbook questions. I know nobody likes doing them, but these are perhaps the most important set of questions I've assigned yet. You really, really, really should do these. Combining transformations is a massively important skill, not just for this chapter, but for a large part of Math 30-1 as a whole. This stuff comes back and it comes back fierce. For other things to do, though, of course, I recognize, of course, you got stuff on your plate, but chapter 1 assignment booklet, we still have several more days to work on that. And then there's a chapter 1 study guide. Hopefully I remember to hand it out to you. If I didn't, just bark at me and I'll get them printed off. But a chapter 1 study guide, it's an outcome checklist. So in other words, it just says what kind of things you need to know. Use it as a checklist. We've covered every single point in this chapter already, except for number 15. That's what we're going to cover next day. We're almost done chapter 1 already. Feels pretty good. Anyway, if you need any help, please make sure you reach out and ask.